So atoms and molecules are very, very small, and we cannot measure their masses. So this is why we use a relative mass in order to determine the masses of atoms and molecules. Relative masses are expressed in terms of AMU, which is the atomic mass unit. And these are comparisons of actual masses to each other. For example, if we have an object that is twice the mass of another object, then simply we can relate those to each other, and we say that the relative masses will be 2 to 1. To define the atomic weight, if you look at an element, we said that the element is made up of the atomic number and the mass number. So it's nothing different than the mass number. So atomic weight is actually the relative mass of an average atom of the element expressed in atomic mass unit. So in other words, the atomic weight is the mass number of the element. Atomic weights, these are numbers given at the bottom of the box, which is equal to the mass number. So if we have an example over here, according to the periodic table, the atomic weight of nitrogen atom is 14. If you look at the periodic table, it's 14. And the atomic weight for silicon is 28. So this means that two nitrogen atoms have a total mass which is very close to the silicon atom. And then we have molecular weight or molar mass. This is for molecules. So atomic weight is for atoms in the periodic table. And we know that when you combine atoms, you make molecules. So now it's going to be molecular weight instead of atomic weight. So molecular weight, these are the mass of the molecules. And to calculate the mass of the molecule, which is made up of more than one atom, we're going to add the atomic weights of all the atoms in the molecule. So let's have an example. For example, water. We want to calculate the molecular weight of water. Water is made up of a two hydrogen and an oxygen. So two hydrogen elements and an oxygen element in there, right? So we're going to say that, okay, we know that the atomic weight of hydrogen from the periodic table is 1. Let's build up the equation. So the molecular weight here is 2 times the atomic weight of hydrogen, okay? Because you do have two hydrogens in there, so it's going to be 2 times the atomic weight of the hydrogen plus we have one oxygen, right? So plus 1 times the atomic weight of oxygen. You go to the periodic table. So let's pull the numbers from the periodic table. You can use any periodic table you want. You do have hydrogen. The atomic weight is 1.008. This is the atomic weight or the mass number. So 1.0, you can say 1.01. You can round it up. And then the oxygen is going to be 16.00 atomic weight. So let's pull the equation over here. So it's going to be 2 times 1.01 atomic mass unit plus 1 times 16.00 atomic mass unit. So it's going to be 18.02 AMU. So for now, this is atomic mass unit. This means that the mass of the water molecule, which is made up of 2 hydrogens and 1 oxygen atom, is the sum of the masses of these atoms, and this is how you do the calculation. Let's do more examples over here. Carbon disulfide, the molecular weight, you have one carbon, so it's 1 times the atomic weight of carbon plus 2 times the atomic weight of sulfur. Okay, you go to the periodic table, figure those out. These are the atomic, these are the mass number. Okay, so that is going to be 1 multiplied by 1201. This is the mass number for carbon plus 2 times 32.07 for sulfur. So if you look at sulfur in the periodic table, you guys, sulfur is here. So that is 32.07 in there. Okay, this is the mass number, which is the same as the atomic weight. It's an atom, so this is why we call it an atomic weight. So that is equal to 76.15 AMU. H2SO4. So H2SO4 is made up of more elements in there. It's made up of 2 hydrogens, 1 sulfur, and 4 oxygens. So the molecular weight is 2 multiplied by the atomic weight. I'm just going to use abbreviation here of hydrogen, plus 1 multiplied by the atomic weight of sulfur, plus 4 multiplied by the atomic weight of oxygen. Okay, go ahead from the periodic table and go get those numbers. It's 2 times 1.01 plus 1 times 32.07, 07 here, plus 4 times 16.00, and that is equivalent to 98.09 atomic mass unit. Another way to represent the atomic mass unit, we simply represent it by a U. So instead of saying AMU, we just say U in there. So that is a U there, okay? HNO3, this is one type of acid, which is nitric acid. So the molecular weight here, I have 1 hydrogen, so 1 times the atomic weight of the hydrogen. I'm just going to write it down directly. Plus I have 1 nitrogen. The atomic weight for the nitrogen is 14.01. Plus I do have 3 oxygens. You multiply that by 16.00, and that is equal to 63.01 atomic mass unit. Same thing as U. Okay, and now of course the molecules can get more complex in there. So this is kind of like a complex molecule in here, where it has 2 iron atoms, right? And there is an SO4 in there, and this is in the brackets of 3. So what does that mean? See that 3, it belongs to every element in the bracket. So this means I do have 3 sulfur here, and I do have 4 times the 3, which is 12 oxygens. Okay, so that 3 belongs to every element in this bracket, and you do just the multiplication. So this is a 3 times 1, it's a 3, and the 3 times 4, this is 12. So if I want to get the molecular weight, I have 2 iron, okay, molecular weight of iron. I have 3 sulfur, and I have a 12 oxygen. Okay, so that is going to be 2 times 55.85. We got this, get those from the periodic table, plus 3 times 32.07, plus 12 times 16.00, and that is equal to 399.91 atomic mass unit, or unit in there. Okay, now for isotopes and atomic weights. So remember what we said, that atoms, they do exist as isotopes, which is the same atomic number with different mass numbers in there. However, in the periodic table, if you look at the periodic table, you just see 1 mass number. So what is this 1 mass number? It's the average of the mass number of all the isotopes, you guys. Okay, and it does have a formula in there. And the formula is to calculate the atomic weight of the isotope, it's equal to the sum. So this is the sum of the product of the percent isotope multiplied by the isotope mass divided by 100. Those normally are given. So you go ahead and you multiply them, you add as much isotopes as you have in the question, and then you get the atomic weight. Whatever you get, you guys, has to be exactly the same as the atomic weight in the periodic table for that element. For example, see here I'm talking about boron. I want to find the atomic weight of boron. So I look at the periodic table over here, and I know that boron is 10.81, right, in the periodic table. So my calculation had to lead to a 10.81 answer, okay, for all the isotopes of boron. So here you go. So it says that the element boron consists of that as much isotope percentage, boron 10. So I'm starting with a boron 10 with a mass of this much. So boron 10 has isotope percentage of this much and a mass, isotope mass of 10.01 unit. So this is going to be over here. This is going to be the first isotope, which is boron 10. Let's go ahead and highlight that. There's another isotope, which is boron 11. And this is going to be the sum of these isotopes. So for boron 10, the isotope percentage is 19.78. We're going to go ahead and multiply it by 10.01 atomic mass units. Okay? Plus, this is what the sum means. This is what this sum over here means. So I'm just going to add all the isotopes together. So the second isotope has a certain percentage, which is 80.22%. And we're going to multiply this by its mass, which is 11.01 units in there. This whole thing is going to be divided by 100. You do the calculation in there, and the answer is going to be 10.81 atomic mass units, which is the same as units in there. This it matches the atomic mass of boron in the periodic table, which is 10.81. Let's have another example. This type of formula is the same, so you're gonna apply it every time the same. It's just like a matter of getting used to just putting the numbers in the equation. So how many isotopes do we have here? We have chlorine 35, we have chlorine 37. So we have here two isotopes. So for chlorine 35, the percentage is 75 and the mass is this much. So let's go ahead and multiply them with each other. This is the percentage multiplied by the mass, 969, plus for the chlorine 37, this is the second isotope. It is made up of 24.24%. Let's put the percent over here. Okay, multiplied by 36.966, and the whole thing is divided by 100. So please don't forget to put 100 in there. And the answer is 35.45. This number needs to match the atomic weight of chlorine. So let's go ahead and see if it's the same. You know, this is a chlorine over there, and it is 35.45. So the mass number that you see again in the periodic table, this is equivalent to the mass of all the isotopes of the element. This is a third example in there, which you are going to do it the same. We have copper 36, but here I'm representing the copper in a different way. I just want you to be familiar with that. So copper 63 and copper 65 in there. These are two isotopes of copper. So you have the percentage and the mass for one, and then you have the percentage and the mass for the other. Multiply them, sum them up, divided by 100, and you get the atomic weight of copper. We're going to check it in the periodic table, 63.55. So copper is here, and it is 63.55. So whatever atomic weight you get is going to be exactly the same atomic weight for the average of all the isotopes.